these two very good lectures before me. I'm very glad that I don't have to explain a lot of the different things. I agree with all the things that have been said, and I hope it will complement to the discussion generated by the first two lectures. So I'm going to talk about more like a process systems engineering approach to chemical substitution. And process systems engineering approach means also how to solve problems. So I have to get this going. Okay. So I will start. There may be some slides that are overlapping with Dr. Razia's presentation because some of the things we worked on together. So I will start with what I call the product process chemicals connection. What you see is in the outer circle on the left, the kind of chemicals-based products we need in our daily life to sustain ourselves on Earth. And in the center are a variety of chemical processes that will manufacture these products that we need. So from my point of view, then we have a problem first of selecting what product to make, and then identifying which raw materials to use, and then finding out a process that can manufacture the product in a sustainable manner. So in that way, actually it includes some of the things that Dr. Overkash was saying with respect to LCA and things like that. So what is the chemical connection? Chemicals are part of the product, and chemicals are also part of the process because either they're being converted or being used as a process fluid. So we have chemicals in all aspects, and some of these chemicals may have undesired health, environmental safety impacts, or compared to a competitor, we could say that we can improve the process by replacing one or more of the chemicals. So the business issue can also get into it in terms of chemical substitution. So that's what I would say, the product process connection with the chemicals. And then I could say that, okay, if we have now established the connection of the chemicals, then we can say the substitution problem is to identify, in one case, the harmful chemicals that can be one or more. So we may replace only one of all the chemicals or may replace more than one. And that harmful chemical can be replaced in the process, which is not part of the product, or can be part of the product. And then we will substitute these chemicals with less harmful but acceptable chemicals, performing the same function as the original, maybe even better, before they, of course, cause any harm to the public. So in this case, also, just like Dr. Overkash has mentioned, we are also looking for a better product or process at the same time. So then what is the challenge? The issue, as we talked about, are the chemicals. Some of them could be harmful because of different reasons, or maybe other chemicals could have been used to make the process or the product better. The objective then is to identify which chemical needs to be replaced, either because it's harmful or because it's not performing efficiently, and what should be those substitute chemicals. So that's the challenge, sorry, the objective. The challenge is how to find that. And compared to, again, the previous lectures, I would say here that, yes, the company who would like us to solve this problem can give us some candidates, but we can also generate candidates. And then, so the challenge is how to identify first the chemicals that can be replaced because of different reasons, and how to find new candidates that will work better. And the constraints, So from a process systems engineering point of view, we have objective and we have some constraints that we need to satisfy. If we look at some databases, I think this was also mentioned by Dr. Rasia, from what we have seen is close to 1 million chemicals that are either being used currently or have been used before. They have been identified at least. And then for less than 10% of these chemicals in the databases, there are properties related to harmful effects that have been measured. So in a way, one can think of that we are, without the data and the knowledge, we might be flying blind. The pilots have autopilot features. Can we provide these autopilot features through some computer-aided model-based systems? So measured data comes from different sources also and have consistency and uncertainty issues. I think definitely also with respect to LCA and other, there are different databases and also different sources of databases and locations that can have a question on uncertainty and consistency. And then because there is not enough data, we need property prediction models. And those that are reliable cover a small percentage of the needed properties and also application range with respect to molecules. Current methods use a combination of experiments and database search, thereby may miss the better substitutes that we may be looking for from a business economic point of view. So these are some of the constraints. There are many more, and that is the challenge that I have mentioned. So now there are historical examples for this also in terms of chemical substitution, and Dr. Razia had mentioned the refrigerant example, and I will try to give a story which I call the swan duck story. This actually happened to me when I visited a multinational company, their research center. And after my presentation, the host took me out for lunch, and they said that we will have our lunch in our very nice location outside, where there is a small room where we can sit and we can look at the pond and the beautiful ground. And in the pond, there were some swan. There were also sitting areas all around the pond for people to sit and have their lunch or others, but nobody was sitting there. And before I asked him why, my host actually told me that this pond looks very nice with the swan, but there is a story behind it. And it was that when we first came, there was nothing, just the pond. We decided to have some sitting area. And then after some time, people started saying, maybe we should have some ducks so we can see the ducks and enjoy the view. So they got some ducks, and very soon afterwards, the ducks multiplied and they made noise, and all the area around the water where they were sitting and having their discussion or lunch, they became dirty. And so they could not use that place anymore. So then there was a kind of a competition made. Who can propose a solution for this duck problem without killing the ducks so that we can use the land again? And the solution was that why don't we get some swans? And the swans would then chase the duck away, and we can sit again very nicely and enjoy the view with the swan swimming in the water. Everything was fine, but after some time, the swans had children, and the swans became very aggressive and possessive for their children, and which were on the ground. And so anybody going close to the ground to sit and eat, the swans would chase them away. So then people were sitting outside into the room where we were and enjoying the view, but could not do what they wanted to do. So that seems to be matching very well with the refrigerant replacement. 1834, the natural refrigerants were fine, but they had some problems of safety and toxicity. And then they were replaced in 1930 with CFCs. CFCs were not dangerous from a safety point of view and were not toxic, but we didn't know that they had ozone depletion problems. So we replaced CFCs with HCFCs, and they didn't have the ozone depletion problem, but they had the global warming problem. And now we have gone to HFC, which has lower global warming problem, and it looks like we have better safety and better control. So we are going back. So all the time, it looks like we didn't know something, and we thought we had the best solution, but we didn't. So that reminds me very much of the swan and duck story that I had listened to and seen. The same could be said also with respect to solvents. And we have solved this solvent substitution problem a lot for many companies. And in many cases, it was not for the harmful effect. It was actually to find a better solvent from an economic point of view. But in some cases also that before a solvent was being regulated, they wanted to find an alternative. So solvents is a good example also, and many times you find one replacement solvent which seems to work on many cases, but then when you expand the analysis horizon, you see that they have problems. Also, green chemistry, we will talk about later, says that we should not use organic solvents and we should use water. But water does not dissolve, I would say maybe 50% of the organic chemicals. So we are limited to where water could be used. What about ionic liquid? They're supposed to be liquid always. They will not be a problem with respect to VOC, volatile organic chemicals. But many applications of solvents does require the solvent to vaporize, like product delivery and things like that. So one actually needs to also look at the role of solvents. So a lot of issues need to be looked at. Okay, now let's look at some of the data issues. So we have collected data for hazardous effect. And then we have looked at that the hazardous effects are classified mainly into 4 main classes. And within the 4 main classes, there are different subclasses. And counting all the subclasses together, there are 33 subclasses. The number you see, 20,325, this is the number of chemicals for which these different hazard effects have been reported. So first is the health hazard, and there are 9 types of subclasses, and the number at the bottom, 17,875, is the number of chemicals for which we have some health hazard data. Then the physical hazards, and then the environmental hazards, as Dr. Razia said, it is only 2, but actually we have more data on environmental hazards from US EPA. And then other hazards definition. So what we say is that there is a database with about 20,000 data chemicals for which we have no data. Most of these data are actually qualitative, not quantitative. We do not know exactly what is the amount that will cause the problem. We know that it will cause a problem. So it's qualitative data. Also, hazardous effect data in terms of scoring system and categories. The global let me remember, global harmonized system. That one has categorized chemicals into 5 different categories. And number 1 is the severe, most severe. Number 5 is the least severe. And there are many that are not categorized 1 to 5. Some of them maybe have not been studied, and so we don't know. And some of them have been studied, and they are not in any category. And so here are some examples that in each of those subclass of hazardous effect, there are categories 1 to 5, and then given in terms of what would be the amount that should be controlled. So these numbers are there. The question is, how do we use it? The good thing about it is that if we collect all the data from different sources, this is about almost 900,000 chemicals. So that's very good. We have a lot of information about these chemicals. What about other properties like chemical use? Which are the chemicals that are being used for different applications? So here we could find data for 43,000 chemicals, which had 174 main classes of use. And you see in the column under chemical uses, some of the main classes of chemicals like manufacturing, additive, food, pesticide, cleaning fluid, so on. And then in the next is how many chemicals have been reported in that, and then you see some examples. There are 174 different types of uses, and within those classes, 825 subclasses. So it covers a wide range of chemical use, but remember that compared to the GHS score data, which had nearly 900,000 chemicals, there is only 43,000 here. And then there is the question of classification of the chemical types. And there are different classifications, of course, possible. One classification from a product point of view or substitution point of view is to classify them according to their uses. We call it also chemical type. So if we are looking for refrigerants, we can go and look for refrigerant chemicals. If we are looking for pesticides, we can go and look for pesticide chemicals. So like that, we have created a database with collected data from different sources. And this one has, I don't remember exactly now, but around 80 or 90,000 chemicals that have been listed and classified. But in addition to this, we also do a classification in terms of what kind of molecular type it is, like hydrocarbons with hydrogen and carbon, polar associating with oxygen or nitrogen atoms, or polar non-associating, halides, steroids, multifunctional amino acids, water. This is just the organic part. We also have the inorganic part. And we will see that this kind of classification has different requirements and different, they also provide different kind of information to us. So if I put everything together, we have a master database with around 900,000 chemicals, of which 48,000 approximately has properties. It doesn't mean that 48,000 has all the properties that we need. Some of them have only one property, some of them have 17 or other properties. The hazardous effect with respect to GHS and also the the different classification of hazardous effect, and then the chemical use. So that's the 43,000 that I was talking about, which is like manufacturing and things like that. So here is the opportunity if from process systems engineering and others want to develop something that others can use, opportunity to develop a structured database for easy search and or retrieval of data, maintenance by developing suitable ontology to represent the knowledge. It should be possible to search in the forward direction, giving a chemical, find all the information, or in the reverse, giving the information with respect to effect, hazardous effect or property or use, and find the chemicals. Both should be possible. And here is a kind of an example of the classification of properties and what kind of properties are needed. The first one in the first column you see on the left are what we call primary properties. Every molecule has one value of this property, and this value is connected to its molecular structure. As soon as we know the molecular structure, we can calculate this property. The secondary property can also be related to the primary, but it is not directly related to the molecular structure. It's also related to other primary properties. So for example, the heat of vaporization, we can calculate it at a given temperature as a primary property, but also we can, knowing the boiling point, we can calculate the heat of vaporization. So like that, the secondary property needs some other properties to calculate. Both are pure compound properties. The next is the third column, where the property, again, it is pure compound, but it is a function of temperature pressure, like density, heat of vapor pressure, thermal conductivity, viscosity, diffusion coefficient. All of these are functions of temperature pressure for the pure compound. So those are kind of properties are also needed. Vapor pressure is very important if we wants to know about VOC and things like that. Then the next two columns are for mixture properties. In one case, the first one, we have a mixture which could be liquid, which could be vapor, which could be even solid mixed, where the phase is fixed, the composition is fixed, and our composition is not fixed, but composition, pressure, temperature may change, and we want to know what is the property of that mixture. So just like the pure liquid density, it will be a pure mixture liquid density. Just like a pure vapor pressure, it will be a pure saturated pressure of the mixture. And then the second last column on the right is the phase equilibrium related properties, because we may have liquid and vapor in equilibrium. Then there are properties related to that. So those can be related to just physical equilibrium, but also chemical equilibrium, also evaporation rate, water solubility, octanol water partition coefficient. All of these are put under this. And finally, what we call the environmental properties. So this is where we add more information to the hazardous, environmental hazardous effect, because we have toxicity, global warming, ozone depletion, bioconcentration factor, permissible exposure limit, and so on. So these are all the different properties that can be needed. And in our database and corresponding property model, we have about close to 100 properties and their models. So now let's look at the opportunities with respect to database. As we talked about, we have a master database with different sets of property. So these are, one could say, different parts of databases. And we need an ontology to represent the data. as well as use that ontology for search engines, both forward and reverse. And just to give you an example of the kind of ontology we are talking about, the property is broken up into 4 main parts. Functional. Functional again has 3 different parts. Then secondary, primary, hazardous. And then together with the properties, we also have the chemical type. And then we need to connect the property with the chemical type. So chemical type can be organic. And within the organic, we have alcohol. And within the alcohol, we have primary properties that we need to connect. And so as soon as somebody says we need primary properties, we connect the 2 parts of the database. And then the last taxonomy or the leaf of this structure is the frame where we have the properties. So we can start from the right, from the properties, go back and find the chemical and what type of property it is and what kind of application it is, or we can go the forward way, giving the chemical, getting the property. So all of these are possible. Including with them are the models that would be needed, not just the data, that if we want to predict the property, which would be the model. And the model would be also classified according to functional, secondary, primary, hazardous. And similar kind of structure is needed for the hazardous effects and the chemical use. So those who are interested in knowledge representation and large data handling, this is an opportunity for them. Now let's look at the question of the gaps in the property. So we had around 48,000 chemicals for which we have 17 of the, let's say, the primary properties. At this moment now we have 25 primary properties, and this has increased to more than 48,000. But let's take this one. And then you can see that the one that has the most property is the octanol water partition coefficient. That is around 15,000 chemicals in it, and that covers around 30% of the database. If we compare it with the water solubility, that has around 2,000 compounds. It's just the one lower below the octanol water partition coefficient, around 2,500 chemicals, and only about 5% of the chemicals are covered. So we need a model so that we can cover all the gaps. Or we need some machine learning or deep learning methods that can tell us how to get the properties, how to extrapolate from this database. And this is just a problem of primary pure compound properties. We have not talked about all the other properties, but let's look at the mixture properties. If I take that we have 48,000 chemicals, then if we want to make a binary pair, possible binary pair of all possible binary pairs of these 48,000 chemicals, then the lower triangle shows the unique binary pairs. So it's not the full triangle we need, we just need the full rectangle we need, we just need the triangle. So that will be the number of binary pairs that will be generated from this number of chemicals. From the data that we managed to collect, we see that we have less than 1% of the possible binary mixtures. So there is a huge gap there. And how do we fill that out? And again, if we are involved with some chemicals that are falling in other areas, how do we cover that? So opportunity to fill the gap is there. So I talked about also that different classification in terms of molecular structure. This is very useful because if we say hydrocarbons are non-polar, and then we have polar associating, polar non-associating, like this, then you can see that we have non-polar is NP, Na is non-associating, AS is associating and NA is non-associating. And if we make different combinations of this, then we found binary data people had collected, and we calculated the excess enthalpy, excess Gibbs energy, and excess entropy, and tried to see where they fit. And then we can see that based on the data, most of them are very close to the axis where the excess enthalpy is 0. Those are quite well-defined mixtures. As long as they are away from the axis, these are more difficult mixtures. They will behave more non-linearly. So data collection is important, and I think many of the chemicals that may cause problem are going to be outside those axes, and people are not measuring the data, or maybe it's difficult to measure those. So that's a problem. But when we are trying to make mixtures, we can easily say that if we make a binary mixture between two nonpolars or between the same kind of associating compounds or non-associating compounds, they would probably be falling on the axis, and we can assume some kind of excess entropy or Gibbs energy values. And if those excess properties are negligible, then the mixture will behave more linearly than others. And this is another way of showing it. So classifying the compounds like this and preparing their binary mixtures gives us some idea of extrapolating from the data. And then we need models. So as I mentioned, for temperature-dependent properties, for pure temperature-dependent properties, we need correlations. And to get the correlations, we need some data which we can fit. That data can be measured or can be generated by a model. Mixture properties, we need model or measured, but there are models that can be used to generate those mixture properties, and as well as the pure compound temperature pressure dependent properties. And those kind of models actually need the primary properties and secondary properties. So if we have good primary and secondary properties, we would be able to generate all the missing functional properties, as well as the hazardous properties. But hazardous properties sometimes are not connected to the primary, secondary, or functional. They have to be correlated directly with the data. So we have the means to do the calculations, but what we need are the primary and the secondary properties as a start, and then that could be a very good start to fill out the gaps. So again, the challenge, we need model development, which will require regression of model parameters. We can use deterministic optimization, minimizing the least squares, or stochastic, so maximum likelihood or Bayesian kind of method. The issues are how many parameters should be there, extrapolation outside the parameters, estimates of uncertainties, all of these. And again, people who are interested in deep learning, machine learning, AI, there's good opportunity for them in this area. So opportunity for machine learning AI, including deep and reinforced learning, is possible to generate this kind of models. I'll give you an example of our work. We have generated, let's go back, primary properties and hazardous properties, a total of 25 properties, and that is given in this publication. It's a group contribution method. The groups are formed, and there are 425 groups. These are not all shown in the figure. Only a few groups are shown. The groups are combined to form the molecules. And if we know which groups are in the molecule and how many of them, then we can regress the parameters. And then once the parameters are regressed, we can calculate the properties, which is very simple and it's good. But with the deterministic method, we can get 90% of the data fitted to around 10% accuracy. In many cases, 10% accuracy is not enough. We need 1% accuracy. And 1% accuracy can be obtained if instead of deterministic, we take stochastic and use machine learning. We can get 90% of the data to an accuracy of 1%. And the same can be done for mixtures, where now we need the group-group interaction that needs to be fitted through measured mixture data. And that's where a problem comes, because if we look at the group-group interaction, again, we need only the lower tridiagonal. Not all the groups are shown here. About 200 of the groups or less than that are shown here. And the white blocks that you see are where groups are not available. That means the interaction parameters are not available. And they are not available because binary mixture data are not available. So you can see that even if we have a group contribution method, without the group-group interaction parameters, we are not able to predict many of the mixtures. And if instead of group-group interaction, we wanted molecule-molecule interaction, we would need much, much more parameters and many more data. So this is the least data we need. This is the least parameters we need, but there is a lot of gaps, and the gaps are there because there is no measured data. So let's assume that we have the database, we have the property models. Now we need a methodology. So the methodology I've divided into two parts. The first is for case one, where we have the details of a product or process. We need to analyze and find out whether any chemical has any problems or which chemical candidate is the best. Similar to the problem that Dr. Overcash had shown, that we have the candidates, we want to analyze and find out which is the best, or if there are problems with them. So, of course, it can be expert knowledge combined with experiments, expert knowledge combined with database search experiments. Also, the method of that Dr. Overcash had mentioned. I didn't know about his method before his lecture, so there is a third and many other options. So then what this will do is, based on the data, we'll find out what kind of hazard category, if we are trying to look at the hazards, what kind of hazard category all the chemicals have, and whether they violate any of the regulatory limits. That would be one thing. At the same time, we need to find out what are the properties that define the product or the process, and whether they work, and whether any alternative is providing better the target functional properties, not just the hazardous properties. So the challenge, how to interpret the data, the CPL hazardous level, the CPL hazardous grade, GHS grade, regulatory limits of OSHA, EPA, REACH, how to interpret the data and predict, and also predict the missing data, together with combine the overall picture that it is not just the hazardous, it is also the economic, it is also the improvement of the product or the process that needs to be looked at. But here we are given the candidate, we are not replacing, we are just selecting or telling what the problem is. And here I will introduce the issue of solvent uses and solvent substitution. If I look at the green chemistry, in one of those green chemistry issues, they said we should avoid use of solvents, especially organic solvents. Also, we should, if we need to use, we should use environmentally benign and safe, easily separable and safe, zero volatility. If we look at the implication, avoidance, Can we avoid solvents? If we want to avoid solvents, we need to find reactions, we need to find separations that do not require solvents. Unfortunately, we have not found them yet, so we need solvents. About environmentally benign and safe, can we use water or green solvents? Water, as I said, many compounds are not soluble in water, so water will not solve all the problems for us. Green solvents, yes, but a different category. If I look at the database from different companies, which some companies gave me, a green solvent for one company was a red solvent for another. So there is inconsistency. Easily separable and safe. Supercritical solvents like CO2. Yes, this could be a good idea, but supercritical solvents operate at high pressure, so there is an application limit. Zero volatility. Use solvents like ionic liquids, but ionic liquids do not vaporize. That is very good. But many solvent applications need the solvent to vaporize in order to deliver the product. So we have a problem. So yes, there are lots of green chemistry issues that can be looked at, but these are not the only issues. Economics, environment, everything need to be looked at, as Dr. Overcash also mentioned. So then we look at the second kind of problem, where we have identified that there is a problem. Now we want to replace that chemical, one or more, in the process or product, and that will then remove the harmful effects or make the product or process better, economically, environmentally, whatever. So we need a systematic, integrated, model-based method that will include the database search, the model base. As Dr. Overcash has also indicated, we need the process model, we need the product model, we need the application of the product model. So if we have a solvent, we need to know how the solvent is used in the process and how the solvent is made. If we have a drug, then we need to know how the drug is made, but also how the drug performs when it is applied. So all of these things need to be looked at. A paint example is very good, because when we take a paint, we have to look at all the chemicals and apply it and make the chemical, the product. But when the product is applied on the wall, let's say, the solvent has to deliver the pigment on the wall and vaporize out. And there is a vaporization rate that needs to be looked at. And the volatile solvent should not be toxic, carcinogenic, and so on. So all of those things need models, and therefore one needs a collection of different models. So that's why it should be a systematic, integrated model together with database, and then experiment also is needed, which you will see. So the opportunity for PSE is to demonstrate its ability to manage the complexity, because it's a complex problem, and to provide the glue that combines everything together to solve the problem systematically, reliably, and efficiently. And also, what I would say is that we should be able to generate promising candidates very fast through computer-aided techniques, and then we should perform focus experiments to verify and select the candidate. So rather than perform blind trial and error experiments, we use the computer-aided techniques to generate very fast the candidates, and then we do focused experiments to verify the candidate. So I'll give you some examples, simple examples now. As I said before, we want to identify and replace the harmful chemical or find a chemical that is better. And so the problem is to replace the identified chemical. And this kind of problems have been solved, and within our community of process systems engineering, it's called computer-aided molecular design, CMD, and I will give you some examples. So here is an example first conceptually. If we start from the top left, and I'm saying that benzene is a solvent, that is very good in terms of solvent properties, but because of its EHS properties, it cannot be used. So I want a acyclic alcohol, ketone, aldehyde ether with solvent properties similar to benzene, but not any of its bad properties. So actually, by selecting already acyclic alcohol, ketone, aldehyde ether, I'm avoiding all those chemicals that will have EHS problems. Then how do I make alcohols, ketones, aldehydes, ethers? I take the groups, the atomic groups, that is CH3, CH2, CH, these kind of groups. And if I combine them, these groups together, I can make molecules. So then I need a method by which I can generate molecules from the groups. And once I've generated molecules that satisfy all the chemistry rules, then I have a stable chemical molecule. And using, again, a group contribution method, I should be able to calculate the properties. And then I can check all the different properties. And if I have more than one chemical that I have generated, I can check which chemical is good. So what I do is I define the substitution problem in terms of product function, process needs, EHS properties, then I apply generate to generate the molecule, and I apply the test to test the molecules and find out which are the best. This can be done, as I've discussed now. We can set up a mathematical optimization problem and solve an optimization problem. It all depends on whether we have all the equations and how do we solve it. So just to show you again how this CMD works as a framework, we start by telling what kind of problem we want to solve, what kind of target properties we want to match, what kind of target properties we do not want to match, which functions we want to improve as an objective function, and so on. So we convert this description of the problem into a mathematical description with models and constraints and equations. And then we solve the CMD problem, that is generate the molecules with the groups, and then using the group contribution kind of property models as the first step to calculate the properties. And once we have calculated the first set of properties, all the others can be calculated from the primary properties. So solutions of a CMD problem then, as you can see from this figure, is iterative, because if we get a lot of candidates, then maybe our constraint was too loose and we can tighten it. If we do not get any candidates, then maybe our constraints were too tight and we can loosen it. And then we do the experiments. And if in experiments we find none of them satisfy our requirement or validate the predictions, we can go back and reformulate the problem and restart. So there is a lot of models needed, a lot of computations needed, and that's the handling of the complexity. But some of these problems with respect to single molecule products have been already solved, not just as a design problem, but also as substitution problem or improved process product problem. So here is an example of a refrigerant substitute. We just want to replace one, find single refrigerant. So we give what kind of molecules we want. We want acyclic compounds, we want isomers, we want fluorine, chlorine in it, and so on. Then we generate the molecules. We generate, in this case, 385 molecules, and we find only 5 that matched our requirements. Out of those 5, only 3 that we could select. And here is a example of the molecule and the chemical formula and the properties that we gave. We gave critical pressure, critical temperature, thermal conductivity, thermal liquid density. So as a starting point, these, and then these would be used in the refrigeration cycle simulation and so on. So that is the first step of the generation and selection of the candidate. In terms of solvents, we have solvents is not just for separation, as you can see in the figure on the left or the text on the right. Solvents have many applications in addition to separation. So when we are looking for new solvents, we need to say why we need the solvent, for which operation we need the solvent. And here is a list of properties, target properties that we may need if we want to use solvent for separation, for liquid-liquid extraction, for extractive distillation, azeotropic distillation, solid separation, gas separation. The first table on the left says what is the essential property and desirable property. So the essential property must be satisfied, because if we are looking for a solvent for liquid-liquid extraction, the solvent must be able to split into two phases. And the solvent must be liquid, the solvent must have a high solubility of the solute, and so on. And then in addition to that, there can be desirable properties that will improve its performance. And then in addition to that, the table on the right gives properties related to health, safety, and environment. So when we are formulating, we need to formulate all of these. And in addition to these, we need to check through process simulation, and after that, through experimental verification. So here is an example, the same problem that was done before. We want to substitute benzene. We give the boiling point, the melting point, heat of vaporization, which is similar to benzene, log P, octanol water partition coefficient greater than 1.5. So it is not soluble in water. Benzene is not soluble in, very slightly soluble in water. It should have high solvent power for phenol, which will be extracted from water. And phenol, one could precipitate out the phenol after it has been removed. So these are all the properties we need. Then we need to calculate, and we again formulate the problem. In this case, we generated 3,065 molecules, 43 were selected. Those generated 120 isomers, and 13 satisfied all requirements. And then because of these properties that we have matched, when we do the simulation will match our requirements, because the solvent power is high, the phenol is able to precipitate out, and so on. Another example with ibuprofen. Ibuprofen is needs to be recovered from the reacting mixture. So we need a solvent first to recover, and then afterwards we need to crystallize the ibuprofen, that is precipitate the ibuprofen from the solvent solution. So first we need a solvent to remove the ibuprofen from the reacting mixture. So we formulate the problem again in the same way. This is the solvent we find. The yellow is not a good solvent. The purple is a good solvent that one can find in the literature. And a better solvent for us is a solubility curve. The curve that you see is a saturation curve. To the left of the saturation curve is liquid. To the right is solid and liquid. So the more we can take the curve to the right, the better. And so the solvent we find that way. And here is the problem formulation again and the solution. So before I go to the methods and tools, our method and tool, I just want to point out, I think Dr. Razia also had shown this, that there are already quite a lot of methods and tools and databases. And here is some of the methods that also Dr. Razia had shown. Also the tools that are available, and also the databases. So what we are doing is we are collecting all of these and trying to make something more systematic, more predictive, more efficient. And this is going to be our tool, which we call Chemsub. And you will see a demonstration of it in the lecture 4 after me, where the database search option will be shown and product analysis will be shown. Product substitution, that is still under development, but at least the analysis will be shown. And the single molecule substitution, I've already shown you that. That's why it will not be shown here. If you are interested in the modeling part, webinar 6 will give demonstrations of the modeling part. For the property estimation part, we will not show them. And also the refrigerant replacement. These were demonstrated in webinars 2 and 3. So today, what can we do if we have the Chemsub tool? We can increase the database contents that we need to do continuously and improve the property estimation feature. There are lots of gaps, we need to fill them. If we cannot fill them with measured data, then we have to fill them with validated property prediction, where we can give an estimate of the uncertainty. Criteria for substitution, as also the previous speakers had shown, we need to analyze and see what actually is the criteria for substitution, and then properly define them. And then afterwards, we need to validate that. So what is the chemical role is very important there. And we have to further develop, let's say, the substitution method and test and verify results. So we want to make a large collection of library where problems have been tested, solved, tested, and verified. Conclusions: confirm the consistency of data and accuracy of predictions is very important. How to fill out the gaps in properties and relate them to hazardous effects and chemical use. What I would say is that the challenges that I've mentioned gives us the opportunity. So because the challenges exist, we have the opportunity, and therefore we can develop things to overcome the challenge. How to interpret the regulation limits, which are also going through changes. Necessary to establish benchmark problems through which models, methods, and tools can be incorporated. Sustainability analysis, including LCS, FT, etc., need to be incorporated in the verification step. And finally, from a process systems point of view, systematic integration of data, models, methods, tools is necessary, and the PAC community can provide the glue to put things together, that is, manage this complexity. So finally, I would like to acknowledge that in the preparation of this presentation, the PAC for Speed Company Thai office, Orakoch, Nichakon, and Siripon provided some of the material. Thank you to them, and also the Chemical Engineering Department, Buet, and Professor Razia and Professor Arafat Khan, Yasir Arafat Khan. They also provided some of the material, so thank you very much. And the last slide contains, in addition to some of the references I had given on the specific slides, these are some references that can be useful for anybody who wants to know more about substitution, solvent selection, refrigerant selection, modeling of properties, and so on. With this, I end. And I see that I'm a little bit over time because I also started a little bit late, but we can see if there are some questions, or we can take the questions at the end. Thank you very much. And I will stop the share so we can see if there are questions. Are there any questions?
I think people are eager to see the demonstration also, because it's self-explanatory, your presentation. Thank you very much.
Yes. Yes, we will start, but I did see one question that was for you, actually, Razia. Somebody had asked, apart from textile industry, many chemicals need to use
Yes, I
for
think
leather
leather,
processing.
yes, there is a person from Leather Institute, and that was one of the concern because leather is chemical intensive. So that's one of the question he
Okay.
had. Yeah.
Does
So
Bangladesh have a big leather industry?
they have, but it's not, I mean, it's not as big as textile. This is the second largest industry. So, and much smaller than textile one. So, but then it's very much chemical intensive. That is the major issue. Yeah.
Okay, so those who are participating and attending, after presentation of the software, maybe you can give us some problems that you would like to solve, some substitution problem. Then we can see if we can solve it. I can see one hand.
Yes.
Muhammad
El
Zarqa.
Zarqa, he's joining from Egypt. Yeah. So I don't know whether.
Can you unmute him so he can ask his question?
Yes, now you can unmute
I'd
yourself.
like to thank all of you for this very interesting webinar and looking forward for more cooperation with you. Thank you very much. All the best for you. Thank you.
Okay, thank you. Okay,
You're welcome.
so let's now go directly to the next presentation. And hopefully after that, you will have more questions. So Orakoch and Nichakon will give this presentation.
Okay.